So then what I'll do is what's called the neutral dissection. So we have some any sort of section from this U sigma to B. So again, this was fibering over this, and you have fibering over this. So you want to find the section. So any section, of course, exists because this is a trivial fibers of course cells, so these are trivial. Okay, so you can find it. So the key point is that you want to change the section so that this is as you flow, it only goes into B0 direction. So that's called the neutralized section. So it doesn't have any B plus or B minus component. Okay. So how do we do that? Okay. Right. Of course, you have any section here, and then you take this differential along the flow. Then because this is a affine bundle, so the differential lies in the vector bundle of that affine bundle. Okay, so that's so because that's what happens if you differentiate the bundle. So of course this differential along this of course this is the flat connection we introduced, and this is just differentiating these phi along this BB. Okay, so any path you can just pull back, and then you take the differential. That is the connection. Okay, so this is connection. And always neutralized section always exists. So this is a standard trick that many people always use. But I guess this is idea due to Rabori. Basically, so you have some connection, and then you have some decomposition. Then you can of course decompose into these three parts. Okay, and by projecting the connection, and then the point is to you add these. Because this is exponentially decreasing, you can actually integrate this, and you can exponentially increasing. You can always do this. So I mean, minus t will be decreasing, right? Increasingly decreasing. So these are two values which are well defined because of the exponential property. So whenever you have exponential integral function, you can always integrate, get a finite number. So we are also doing this over a compact manifold. So these are all going to be well defined. Okay. And the point is, if you do this add and then subtract, then this is actually and then you do the the standard connection. This is just this A minus part and A plus part will vanish. Okay, because this is shown in their paper, but the basic point is if you differentiate this integral, you just left with the this b minus term at the t equals 0, because and then if you do the for the t here, you just get the a plus term. Okay, so it's just taking the minus is here. Okay, so that's the only thing that's happening. So therefore, you can find these sections, neutral section. And so what's nice about this neutral section is that so along the flow, it always goes in the neutral direction. So if you start with some codimension 2 subspace along the A0 direction, I mean V0 direction, some parallel to V0 direction, you never escape that affine plane. Okay, so that means you're always staying there. Okay, so that's the point here. So you can actually define a map from geodesic to some codimension to affine subspace here, and and then these are all equivariant sort of things, and and so on. So you find this equivariant map to these codimension to subspaces, and these are invariant under the geodesic flow, and actually you can define a map from this this boundary of omega times boundary minus the diagonal to this space, okay? Because each geodesic along the geodesic is the same, so you can for each geodesic is determined by these two endpoints. Of course, you have to remove the diagonal. So this is the same as the space of geodesics, anyways. And so this is well defined. So once you have this affine space, what you can define is from the boundary. Actually, you can define what is right. S is the space of pairs X and some hyperspace passing that X in the omega. So for each point X, you can so this is the space like that. So space of pair a point in X, and then H is the hyperspace containing it, and the tangent to this here. Okay, so you can actually define this. Okay, so why? Because uh, actually it doesn't depend on so for geodesic uh, so you can define this map tau for each pair in this lambda star. So the lambda star is what? Lambda star is this. So for this lambda star, you can define this map, but so you just take the initial point and then the initial point and the hyperspace codimension to subspace we have you define a join that two spaces and then you get a hyperplane. So you take the hyperplane containing X and then this codimension n minus two space. Okay, so then this is how you define this map. Okay, right, and then the next we just show that these are actually disjoint from U, and then here we show that it actually depends only on the initial point. Okay, so it's unique for each X. So that's just because because if they're different, then they kind of will be parallel in the affine space, and then the contraction property will contradict this. So they have to be the same. Okay, so then you just take the so once you have affine space, then you take the interior direction to the omega, and then you take the intersection, and this will be how you obtain the U here. Okay, and so you define U like this, and then of course we need to show that the independence of regardless of which you choose here. Okay, so those are also again following the contraction property and so on. So I skip much details here. Okay, and now we can also do this for the case when this is not word hyperbolic, and then the basic point is so the same conclusion we hold, but but for each point you might have more than one supporting plane. Okay, so in the codimension Sn minus one infinity. So for each one that you can obtain these hyperspaces. So you need to define this augmented unit tangent space. So which is that you take the not only the points the vector and the endpoint, but these tangent hyperplanes at the beginning and at endpoint. Okay, so we covered that already, right? So this is again a nice compact space over. So if you take the quotient, it is again a nice compact Hausdorff space over this. It is orbifold. So so it is just some sort of blown up part of a uh, unit tangent bundle. Okay. And then you can also define these limit sets a little bit bigger limit sets. And the arguments are very much similar, but of course, there is some little bit difference here. Okay, but the basic philosophy is the same. Uh, but of course, I did change a little bit here because of some argument problem again, but you see that in the new revision I will put up next. Right. So arguments are very similar. So and then you obtain these. So once you have that, then we get some sort of what you call the lens condition and type. So we have some omega like this, and if satisfy the uniform eigenvalue condition, then you can find the properly convex domain omega there with strictly convex boundary. Yeah, and these are actually smooth boundary, and these you can give you the lens orbifold. Okay, so those. Uh, Okay, and basically, so the thing is that so of course for so the affine spaces are in the both directions. So you find these convex domains on the both directions, and then you have to. So now we don't have a smoothness, but the point is to make this into a smooth boundary, the space, and so basic idea is to first of all try to make this into polyhedrally convex domain. So you cut it into some triangulated space, which is with locally finite triangles. And so to do that, we just need to do some tricks with the hyperspaces, and then we need to finally smooth this. Okay, right. So these are all just trying to show that these hyperplanes that we are using is properly locally finite in some sense, and that's all we're doing. And then you do the finally some sort of a smoothing process of this polyhedral space, and that's what we do. Okay. And the smoothing actually is just done by some sort of applied math technique of smoothing the. So you have some compact polyhedron, then you can always approximate by smooth convex surface. So that's some actually that's a recent technique. Actually, I found that of applied math. But anyway, so you use some functions and you do some kind of a sum to and that differential to obtain these kind of thing. Okay, so let's go to the lens, radial lens now. So these discussions will be sort of dual to the flat uh, lens totally TN case. And so first of all, what is a lens here? So we have some R and of general lens type. And this is just means that there's some lens where PN label, which is just lens joined with lens joined with P, and then sort of things like this, and then so concave ones are the ones which you have to remove the lens itself. Okay, so those are the things, and so so one thing is that so these groups are all so the end groups will be the ones which are convex associated with convex closed orbifolds. So the Benoit theorem applies. So you can either be not a product, virtually not a product of some group, or it will be not have it will be irreducible. Okay, so it's either some so the group itself is sort of has some decompose into some invariant subspaces, or uh, and have some center, and then the or it will be irreducible. So those are the two cases. So if it's factorizable, then this sigma is just going to be join of some properly convex domains, and then these step X on these group co-compactly, but of course the quotient may not be Hausdorff here, and so and then there's some finite index subgroup which is isomorphic to this and GKR. So there's always some subgroup acting trivially on here, which is diagonalizable, and of course those are the center here. Okay, so the irreducible case and the non-irreducible case is just given by the existence of these centers here. Okay, and right. Okay, so let's introduce uniform middle eigenvalue condition. So we have these Pn of the Rp and then Kb these things. So sigma tilde is actually not the something embedded, but it's just the space of rays. Okay, and so these are always have compact quotient on the gamma e uh, these, so let's look at this largest eigenvalue of G divided by the VE tilde, and then suppose these are in between these with some constant, then this satisfy the uniform middle eigenvalue condition. Okay, so actually I think this length can be actually so C here could be replaced by 1, but not here because actually you can show this is true. Because this is actually, you can show that this is the smallest eigenvalue. Okay, so you can prove that in their results. Okay, but anyway, so if you introduce this conjugate word length, so this means that if you have any, so this is true for any group. So you take any group and then you take the minimum word length of any of its conjugate. Okay, then that will be the conjugate word length. Okay, so that's the thing, and then you can actually replace it with some conjugate length here. So this means that uh, um, that this is because this length and these are actually compatible with some bounds by this Spack-Miller theorem. But actually, this is sometimes called Miller-Spack, but Spack is actually a professor in UC Davis because this is his Russian name, right? That's why he wrote this. I mean, this is a bad translation of his Russian name. All right. Anyway, so that's the uniform middle eigenvalue condition for the Rn's, and of course, if you dualize this, then you get our uniform middle eigenvalue condition for the Tn's as well, right? These lambda k star is the ones that associated with the totally geodesic plane. Okay. That's because if you have a fixed point, then in the dual, it will be correspond to a dual plane. Okay, so those are the. So the point is that if you have a Pn of a strongly tame convex report, and then satisfy the uniform middle eigenvalue condition, uh, and then these things, then there is a lens where the action is co-compact. Okay, and X properly discontinuously. Okay. But of course, these lengths may not be inside the omega. I mean the domain, but these o tilde. But actually, you can put at least a generalized length inside. Okay, because you can. I mean, O tilde is always convex, so you can always do that. But if it is a virtually factorizable, like in the Benoit case, I mean, these center, when there's a non-trivial virtual center, then of course, then you can actually do it with the lens. Yeah, so there's improved lens. That's because in the virtually factorizable case, there's always totally geodesic plane containing in the inside the lens. Okay, so that's to be something to be proved later. So the basic idea to prove this is that you dualize to the affine case, and then you get these hyperspaces, AS spaces, and then those will be dualized to some points, okay, in some domain. So let's look at this subgroup which fixes this point E tilde. And so then you can see that this has this form, right? So I do that because I want to make this into SLM plus 1. Okay, so I have to divide these things here. And then there's this map from lambda BE to G to BE, which is just the map from homomorphism from here to there. Then this is the linear part, and So this group will of course sit over this product group by just sending this upper left corner into H hat G. So H hat G is actually this part normalized to have eigenvalue plus minus one. Okay, and then this lambda, and then the fiber. So we have this. But the corner is there's actually Rn star here, okay, because this thing. So there's actually diffeomorphism like this. Okay, so this is of course not group homomorphism, but just diffeomorphism. And then there's some laws like that, and then you can make a module Rn module with this action given by like this, and the point is that if you have this character variety mapping to this group, then this actually maps to this space. Okay, with the fiber is always is homology. Okay, onto this. So this is sort of like the fiber bundle, but it's not a fiber bundle because sometimes this can drop to zero here. But I mean, this dimension may change here. So, but if it's constant, then you can make it into a fiber bundle, I guess. Mostly. These sort of ideas are many. I mean, if you sort of put a restriction like this, then you can always do these kind of things. But I think Porty did something similar in his work also, the recent paper, right? And so we have what you call the tubular. So associated with anything like this, we can obtain something called the tubular action. So that means that if this group acts on omega, then Sn minus one. So if you remove 2 points from Sn, and then you can project this to a lower dimensional sphere by looking at each geodesic segment goes to 1 point, because each geodesic segment connecting B and minus B is some sort of direction at B, right? So you can always do that. So these are projective maps. So tube is, so if you have some domain, then you look at all the inverse image of this, and this will be foliated by these gray segments ending at B and minus B. Okay, so the tube domain will be the union of all these things. And then, so suppose we have this kind of action, then this will act on this tube as long as this linear part acts on the omega. So this will act on this tube. So then the key point is that you have any, so you dualize this kind of action, then the point is that this dual group will act on some affine plane corresponding to V. V corresponds to the hyperplane in the dual, so it will act on, so it will become an affine action. And so the set of hyperspaces in here will correspond to the dual of this Sn minus one, and basically the right what am I right so right, so the basically what I have to do is that the distance gamma action is radial action is in this invariant tubular domain. There's some convex compact invariant set destroyed from the vertices of the tube, and the affine action is asymptotically nice if you have some these AS hyperspaces containing each supporting n minus one space. So these are bounded away from these Sn impedance. So these are compact. Okay. So the point is that if you have this dual action, and then it acts on omega, then it's asymptotically nice if and only if the dual acts in a distance way. Okay, that's because it's the basic fact is that any of these elements of these AS hyperspace correspond to point on the boundary between these boundary segment. There's some point corresponding to it. Okay, so exactly one. So this is a dualizing of that argument, and so you can prove that. Right. And then so for the factorizable case, the reason I can get the totally geodesic subspace is because we have these group actions which decompose, and the central elements will also satisfy the uniform eigenvalue condition, and that will fix some because these are in the center, which is sort of a diagonalizable elements anyway. So you can then use that to show that this lens which you obtain has to be ending on some totally geodesic plane. So these are all commuting elements, and they're commuting set of diagonal elements which everything else has to commute. So therefore you obtain these sort of hyperplane, which is invariant. Okay. Okay, so that's the basic stuff that I did here, and so I will continue on the from 5.3 from next time.